Welcome to today's electronic design webcast. Our topic today, Beyond Date Codes, Rethinking Semiconductor Traceability for Reliability and Resilience, sponsored by Rochester Electronics. I'm Bill Wong, Senior Content Director for Electronic Design. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box, and a member of our team will assist you. You can also click on the question mark help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speakers. Dan Deisz is Vice President of Design Technology at Rochester Electronics. His group performs all authorized product replication and customer-specific design solutions. Daniel is also an active member of the Anti-Counterfeiting Task Force for the SIA, having trained more than 200 CBP/HSI agents. Peter Crudele is Senior Manager of Quality Assurance at Rochester Electronics. He has over 20 years of experience in the manufacturing, process, and quality engineering within the electronics and defense industries. Now let me turn things over to our presenters. Dan and Peter, the floor is yours.
Thank you, Bill. And first of all, I want to say thank you to everyone taking some time today to join us for an hour. Again, my name is Dan Deisz. I'm the VP of Design Technology here at Rochester Electronics. And my partner here is Peter Crudele. And hopefully, please feel free to ask any questions as time goes through. We have a question monitor person going in the background who's going to monitor those questions, and hopefully we'll get to all of them at the end. So for today, we want to talk about, first of all, some context. Where are we coming from with regards to not just traceability or date codes, but also just put some industry context to where we are today, and kind of try to link in the thought concept of traceability, as well as long-term storage and reliability best practices, and go through the technical data that Peter will talk about related to what we found related to date codes and products stored in an authorized channel. So with that, I'll start out with the kind of the market today, and I want to talk about, you've seen these pie charts before from the SIA, from the Semiconductor Industry Association, and really concentrate on the bottom three pieces of the pie. It's really, the semiconductor market today is dominated by the data center, which is about 35% of the market. Communications, which is really cell phones, it's a third of it, and then automotive about 13%, and the automotive piece growing fairly substantially. And the previous years down there, just for reference, as to how the semiconductor market has continued to grow, and it's very easy now to see that in 5-10 years this thing is going to be $1 trillion market, and that's pretty substantial. Everything is turning to semiconductors. But if you really look at what markets are related to date codes and traceability and all that, it's the long-term markets. It's not going to be the data center, it's not going to be the cell phone, it's not going to be those percentage of the markets, which are really about 68% of the market. They don't get into this whole date code or bit because their churn is so fast and their markets are so fast. And so you look at what that leaves is automotive as a long-term market that is a substantial piece of the semiconductor market that really is looking for long-term product, and certainly that's where we get into date codes and traceability and so forth. And again, the three markets that really drive the entire semiconductor market, if you think about it, these are the primary markets for all new product development across the entire semiconductor market. These are the primary ones. Most of the new products in the world are really geared towards selling into one of these. So, another interesting thing about the semiconductor market today that kind of relates to this whole date code and traceability thing is really the top 10 semiconductor companies are two-thirds of the market. Now, why does that matter? It's because more and more of them are fabless, and I'll get into why that matters. And yes, the military market is growing, but the pie is growing at the same rate, which means still uh, defense markets are probably still going to remain about 1% of the market. Essentially, no new semiconductor products are being designed for that market. That they use products that already existed, or maybe the automotive guys kicked out. And today, last little bit here on the market is that we've got, you see the overall market growing, but that's really on the data center side. But for most semiconductor companies, it's kind of flat. It's really not been growing a lot, been kind of stagnant. And we've been in this for a while. Now, of course, we've seen lots of trends. This is from Market Tech Insights. You can go look on what they evaluate the market as, but you can see troughs and peaks in semiconductor market has always been the case, but this has been a very prolonged kind of stagnant market. And that will matter when it comes to date code traceability and so forth. And I'll go further into that. So again, more components becoming obsolete at a faster pace. The offshore assembly and test people, they're moving away from lead frame assembly. So we're seeing a lot more obsolescence when it comes to package types. That's driving a tremendous amount of obsolescence. Pretty much every package needing trim and form tooling. Um, and and while the market has been stagnant for most semiconductor companies, there's a lot of consolidating product lines going on. There's a lot of obsolescence going on. A lot of companies evaluating what are we doing? What are we focusing on? What's it going to take to grow again? Because for now a prolonged period, there really hasn't been a lot of growth for a couple of years now. And I just want to say that you're trying to manage a product through an OSAT supply chain. That's not real manufacturing, and it's not really going to make sure that the product is there for the long term. And I say that because Rochester has invested in a tremendous amount of assembly test in the U.S. to ensure that we still have the availability to ship product for the long term. So you don't have to worry about product availability as long as we can secure the die. And the latest investments, if you take a look at all the latest investments in technology going on, really pretty much everything going on, for wafer foundry stuff, it's primarily been 12-inch. And what does that do? That says everybody who's using all the way down to 1.8 volt technologies has primarily been on 8-inch, not 12-inch. So that means all the new investment that's been pouring in for both assembly and silicon is really leading edge. That's the 69% market, which is more or less portables and data center. That's where the investment has primarily been, not in long-term system market stuff. Okay, last little slide here before we start jumping into date codes and traceability. There are four main reasons for semiconductor product obsolescence, and I think it's important for our customers to understand that there are four separate reasons. When you get a last time buy notice and that's delivered to you, that's only part of the story. And you're not going to find this out if you're talking through a distributor. You really got to go try to get that data from a aftermarket manufacturer like Rochester, or to the semiconductor company directly. And those four main reasons for product obsolescence, and again, related to date code and traceability and all that, is product longevity. And that's the reason I'm kind of painting this picture here. Silicon obsolescence reasons, package obsolescence, tester platform obsolescence, and very simply revenue targets not being met. And each of these four categories tells you something different, tells you the different actions that you must take. And if you've got questions about what that is, please get with us and we can walk you through what each of these means or what it gives you for options. All right, now shifting gears into some data we've gathered, we went out and did an industry survey on date codes, traceability, and quality, and really almost 80% of everyone who replied came back with traceability and quality as primary concerns, and kind of look at who the audience was. It was EMS, electronic manufacturing services, original equipment manufacturer, and and they, their number one is age and compatibility. I'm gonna get into that, or Peter will get into that as well. Lead finish, that's probably related to solderability and how the part's going to go on the board, and Peter's going to go into that a little bit. And then reliability and electrical performance as it relates to the product. And so these are all kind of related, date code, traceability, and quality. And we'll kind of paint that picture with the technical data we did. If you look at the industry standards surrounding this, date codes, traceability, and so forth, and product storage, it's JEP 160, J Standard 020. These guide kind of your storage, moisture sensitivity, conjugate mitigation. AS 6496 is fully authorized sources, meaning the product never left the authorized channel. That's really every product at Rochester Electronics. But you got to dig in with whoever you're buying the parts from to find out if they are AS 6496 to be ensured they never left the authorized channel. And that matters because product storage matters. And product storage, what we're going to be talking about today, is product that has never left the authorized channel, 100% authorized. And what TI talked about in their long-term papers that they've written is fully authorized, never left TI's channel. And so all the data we're talking about where date code really, the old date code metrics are irrelevant, is really referring to product that never left the authorized channel. And that's a really important distinction, which is why we're bringing up this AS 6496 here. Um, and we believe that you can improve supply chain quality through standards, and right now on date code there really is no standard. I want to make that clear too. All right, let's talk a little bit about date code history of kind of a timeline here, and also keep in mind that across this whole timeline, it used to be kind of a common thing that, oh, 2-year date code, we don't want anything older than 2-year date code. Why is that? Where did that come from? What's that based on? And if you really go back in time, you go all the way back to the 50s and 60s to find that. That's really where it came from. It and in that time frame, semiconductor process technologies and assembly technologies were really primitive, incredibly primitive. And yeah, date code could have mattered a lot more. And if you look into the 50s and 60s, there were the primary market at that time in the 50s and 60s was actually military. So this is where the whole date code thing started. Fab process not as robust as they are today. Assembly processes not as robust as they are today. The primary market driver was military, and now it's the 1% market. And that's where this whole date code thing originated from. And yes, there were reasons back then that made a lot more sense from a material perspective as to why date codes or why fresh assemblies were more important than today. And I wanted to paint that picture as to where it came from, because it's important to understand where this all came from. A lot of times we're dealing with stuff, well, I don't know, that's how it's always been. And we believe date codes is just that. That's how it's always been. There's another reason for date codes, and we'll go into that when in the conclusions when I come back to you. That is primarily money related, and we'll go through some of that. So, kind of a preface to all the technical data, and now at this time I'll turn it over to Peter.
Thanks, Dan. Thanks for your insight into market trends and supply chain considerations. As Dan said, my name is Peter Crudele, and we appreciate all of you taking the time out of your busy schedules to join us here today. As Dan previously mentioned, this is the third and final installment in a series where we evaluated age components. And I'd like to start off with a brief overview of our previous study, looking at the effects of long-term storage on semiconductor components. It's kind of a preview into our current study. And in this study, we evaluated the performance of components that were in long-term storage from both an electrical and mechanical standpoint. In evaluating electrical performance, the components we looked at were up to 17 years old at time of test. And they covered a variety of lead finishes from matte tin, tin lead plate, and nickel palladium gold. All of these devices were tested to their respective datasheet parameters with 100% yield. Now, in order to evaluate the long-term mechanical integrity, we reflowed components of up to 16 years of age directly onto FR4 boards, with corresponding LAN patterns based on the appropriate package outline. The devices were used as is, directly out of storage, with no additional pre-cleaning or device preparation performed. The assemblies were inspected using non-destructive techniques, basically visual inspection IPCA 610 criteria, which is for electronic assembly, and additionally X-ray. Subsequently, we proceed to cross-section and perform SEM analysis on the various mounted components, and using these inspections and analytical techniques after board level assembly, no construction or reliability concerns were identified. It is important to note that maintaining good practices for storage, which may include utilizing moisture barrier bags, desiccant, and humidity indicator cards, especially for moisture-sensitive devices, helps mitigate risk. Looking at the non-destructive samples, and starting with the image of a board-attached PLCCs and T-SOPs on the left, we see solder coverage that's compliant to IPCA 610 Class 3 requirements. In the middle image, a top-down X-ray of a T-SOP, there's no indication of any bond wire-related anomalies. And then moving on to the right, it's more difficult to see the bond wire to lead finger bonds, but we can see sufficient solder filleting between the leads to the LAN pads. We then took the assembled boards and performed destructive analysis, including decapsulation and cross-sectioning, followed by SEM. The PLCC on the left was decapsulated and SEM imaged, showing no issues with the wedge or ball bonds. And if we look at the middle, we cross-sectioned and SEMmed PLCCs and T-SOPs, and in both instances, the internal structures do not show any delamination along the interfaces. That includes between the die attach, mold compound, lead frame, bond wires, and the die itself. The image on the right is of a PLCC that was cross-sectioned directly through the center of one of the J leads. There is clear indication of sufficient solder filleting up the toe and heel of the lead to IPCA 610 requirements. At the end of the day, this study was able to demonstrate that using standard board mounting processes, we were able to take devices over 16 years old and successfully mount them without issue. So when we talk about solderability testing today, the most widely referenced specification is J Standard 002, solderability tests for component leads and terminations. Another specification that may come up in discussions is JSD 22 B102. which was rescinded and consolidated with JStandard 002 in 2014. Like all standards, JStandard 002 has been updated as industry trends and processes have evolved. If we look at solderability standards as a whole, solderability testing initially focused on dip and look methodology, which long predated surface mount test simulation. In 1998, B102 added surface mount test simulation for tin lead, though lead-free was not included at that point in time. Around the turn of 2003, JStandard 002 included 3 categories for steam aging. These range from no steam conditioning to 1 or 8 hours of steam conditioning, based on what the anticipated usage window of the device was. A device that was intended to be used within a short period of time wouldn't have had any preconditioning specified. But a device intended to be used after an extended period would have used one of those steam aging conditions. The intent of the steam aging is to accelerate the aging of the lead finish surfaces such that it simulates natural aging. As the methodology continued to evolve, B102 was added an alternative method of preconditioning in dry bake, as well as incorporating lead-free surface mount simulation in 2004. JStandard 002 caught up in 2013 with the addition of dry bake preconditioning, basically 155 degrees C for 4 hours. And with this update, 2 additional steam age conditions of 4 and 16 hours were also added, and dry bake was established as the default condition. A year later, B102 was rescinded and considered consolidated with JStandard 002. The current revision of JStandard 002 occurred in 2017, in which the verbiage was added in 4.2.9 that states, actual demonstration of SMT in terms of physical device mounting on printed boards may be utilized as part of solder inspection operation that is performed as part of the documented assembly process in lieu of SMT simulation. So while that's a mouthful, if we think about what that means, it's basically saying that using actual production methods to determine suitability is a viable option in lieu of the traditional dip and look or simulation reflow methods. So we've gone through the evolution of solderability testing, and now we're going to take a look at the different methods, additional details that comes into play into our paper. In dip and look testing, which is intended to resemble wave soldering, a robotic arm is used to dip the devices, initially into flux and then subsequently into a molten solder bath. This is followed by air cooling and a clean. The rate of immersion, depth of the dip, dwell rates, and dip angles are all controlled. With surface mount devices dipped between 20 to 45 degrees, whereas through-hole devices are dipped at 90 degrees. When performing dip and look on dual inline surface mount devices, each device sees a total of 2 dips, requiring devices to be rotated 180 degrees between the dips. For devices that have leads or terminations on all 4 sides, they're dipped a total of 4 times, rotated at increments of 90 degrees. Advantages of the dip and look test is that it's the most readily available and easy to use method. The disadvantages is that it can't support BGAs and it may not reflect an end user's application. Now, surface mount process simulation testing more closely resembles the SMT board mounting process, but there are some differences. With surface mount testing, we start with a non-wettable substrate and use a screen print stencil, solder paste, and a squeegee to generate a land pattern that corresponds to the device being evaluated. Devices are then manually placed on the solder paste patterns, and then the substrate and devices are processed through a reflow furnace and subsequently cleaned to remove any potential flux residue. The advantages of simulation reflow is that it more closely resembles the typical end-use application, but the disadvantages are related to the cost of the equipment and the time and cost to acquire land pattern-specific stencils. Taking a closer look at simulation reflow, a key aspect is producing a land pattern to which the devices are placed on and subjected to reflow. In order to achieve this, a stencil is generated based on the device's land pattern, with design considerations noted in JStandard 002. Basically, the standard gives guidance for a nominal pattern thickness based on the component lead pitch. For lead pitches or spacing between leads of 20 mil, the nominal thickness is 4 mil. For pitches between 20 to 25 mil, it's 6 mil. And for lead pitches greater than 25 mils, it's 8 mil. An item of note is that no guidance is given for the stencil opening width based on the lead width. This can result in variation of paste volume from one stencil design to another between test sites. The solder paste is deposited on the stencil and squeegeed across the openings between a 45 to 60 degree angle as specified per JStandard 002, and this leaves a land pattern for which devices are then placed. After reflow, visual inspection is performed on the devices, looking at the critical areas. For leads, or in the case of leadless, lead terminations, a continuous solder coating free of defects is required over a minimum of 95% in the critical area. On exposed pad packages, the exposed pad surfaces shall have a continuous solder coating free of defects over at least 80% of the critical area. So as we can see in the image for J-lead components, the critical area is twice the lead thickness from the seating plane. However, when we look at the requirements for gull wing components, we see that the critical area is from the underside of the lead to a height of 1 lead thickness. With BGAs, it's different in that each solder sphere shall be incorporated into the paste deposit with consistent wetting and no evidence of surface oxidation anomalies. Moving on to our most recent study, we're looking to evaluate the various solderability test methods that we reviewed here and assess their suitability when applied to aged devices. As part of this study, we look to raise awareness in the industry as to the available test options and their applicability in a given situation. The study also provided Rochester an opportunity to assess our internal board attach capability and compare the results against those of contract manufacturers. The decision was made to focus on surface mount devices covering package and termination types ranging from leaded gull wing devices such as SOICs, TSOPs, and PQFPs, leadless QFNs, and ball grid arrays, also known as BGAs. The devices selected covered a broad range of termination counts from 8 to 240, and for each of these package types, devices were selected that ranged between 8 to 22 years old and covered a distribution of 3 different date codes per package. This was intended to ensure that not only did we capture a mix of commonly used package types in everyday board assembly, but there was also representation across the various age ranges. The testing methods evaluated came right out of JStandard 002. First, we evaluated dip and look and simulation reflow using a total of 3 sites, 2 independent test providers, and internally at Rochester. And the devices used did not go through any pre-cleaning and were used as is. Both steam aging and dry bake preconditioning were evaluated. And then for the next part of the study, it involved simulating an end user's application by performing board attach at a total of 4 sites, 3 independent contract manufacturers, and again, internally at Rochester. For this part of the study, a 4-layer FR4 board with corresponding land patterns for the devices to be mounted was used, and details of the board layers and copper weights are depicted here. All 4 sites utilize the same S1 reflow profile. When we reviewed the results from traditional solderability testing, for dip and look, we found good reproducibility across the test sites, with approximately 29% of the lots having observed defects. In simulation reflow testing, 28% of the lots resulted in having defects with moderate reproducibility across the test sites. The interesting takeaway was that we found there was poor correlation between the two test methods during testing, meaning that in some instance, results for one method may have passed, but when tested to the alternative method, failed. Basically, a component that had failed dip and look passed when tested to simulation reflow, and conversely, when passed to simulation reflow, failed dip and look. Looking at the examples to the right, we can see a QFN that passed dip and look, but failed when tested to simulation reflow on exposed pad coverage. When we think about the methods of the testing and what may have happened, for dip and look, the QFN device shown here was dipped into flux and molten solder along each edge a total of 4 times. This sequence gave additional time for the flux to act and for the solder to wet. For the QFN device run through simulation reflow, taking into consideration that the stencil pattern was deposited onto a non-wettable surface for which molten solder does not have an affinity, the molten solder would tend to flow to the portion of the pad with the greatest affinity for wetting. And looking at the SOIC images, for dip and look, the device would have been immersed in a solder bath for around 5 seconds. So if solder didn't sufficiently wick up the lead-in time, and taking into consideration the surface tension of the bath, an area of continuous solder coverage wouldn't have been achieved. Whereas in simulation reflow, the solder paste has 2 options: remain on a non-wettable surface or wick up the device lead. Overall, the study was not able to correlate failures to a given traditional test method, date code, or package type. And results between dip and look and simulation reflow were not always consistent. Here we see one of the board level assemblies using age components. The QFN shows compliant wetting across all of the visible terminations. The BGA shows solder ball paste wetting with no oxidation anomalies, and the PQFP shows compliant wetting up the leads. From the assembled boards, we perform cross-sectioning of individual components. SEM imaging of the cross-sections focused on the internal bond wires as well as the solder joints. In these images, we can see that the bond wires in the BGA and TSOP examples do not show any anomalies, nor is there any indication of the lamination between the bond wire and mold compound, and there is no lifting of the ball bonds, and bond wire integrity remains intact. The solder joints for both packages appear robust, with no non-wetting of solder, and in the case of the TSOP, there is good filleting up the heel. In all cross-sections analyzed, we were not able to observe any defects. In reviewing the compiled results, these 2 matrices cover both package types and age of devices used in the study. The matrix on the left encompasses dip and look and simulation reflow testing. And while results were consistent within a given method in between test sites, the methods themselves did not always provide the same result. The matrix on the right, in which devices were board attached using production processes, resulted in 100% of those same components and process devices passing solderability and visual inspection requirements at all 4 assembly sites. So we started off by reviewing the background of solderability testing, its evolution as processes and new technologies emerged. We went over the primary methods of solderability testing used today in dip and look and simulation reflow, as well as the introduction of board attach as an alternative evaluation technique. To summarize the results of our study, dip and look and simulation reflow testing is consistent within a given method, but may vary against each other. Utilizing board attach and replicating production processes, we were able to successfully attach all of the devices evaluated in a variety of packages over date codes spanning 22 years old. Finally, board attach is a viable option to assess age devices for being fit for use using real case conditions. And with that, I'll hand it back over to Dan.
Thank you, Peter. Just a quick note for everyone. We have all those white papers that we've done and content for you, and you can download as a result of logging into this webinar. I think that's pretty clear after the when you log in, but nonetheless, those white papers are there for you to download. Let's talk a little bit about. So what Peter went through was a history of what we did and what we showed, concluding in when you actually use board attach, you're going to end up, from what we looked at, 22 years of product date code being viable, and I think that's pretty powerful to say, look, if you bought within the authorized channel, what are you doing with worrying about date code? It's not real. But more importantly, I want to give you some practical feedback, and we've got one that was older here, COVID-19 timeframe. 1 out of 3 of our respondents reported back that date code doesn't matter when the shortage was really happening. And a real world example here within the last 2 months, I'll say, was all of the concern in the supply chain for Nexperia product. Pretty visible, pretty viable, and guess what? Nobody cared about date code. And so date code has kind of become this convenient thing more than anything. I'm going to say we have evidence now in 2 shortage periods within the last 5 years where absolutely date code was not part of the problem at all. Don't care about date code, whatever, just get me the parts. And that is a recurring theme. What that points to is that really date code is a financial problem, and I'm very sure it is when it comes to contract manufacturers dealing with inventory over the long term and committing to systems that maybe there isn't a financial commit to. It becomes an incredibly difficult thing to deal with from a procurement and storage of product perspective. Understand that's real, but that's not really a date code problem. That's really a financial challenge, a very real challenge. But I think as an industry, we need to kind of walk away from, we can't take date code because there's no technical data anymore that exists that says fully authorized product has a date code concern. That just doesn't exist. And so we're open to any kind of discussions or challenges along those lines, but that I think then points to fully authorized traceability and making sure that your product really was in AS 6496. And then if it's not, of course, you're going to have storage. And thank you for advancing the slide. Why the 2-year date code rule is obsolete, we've already talked about it. Origins of the 2-year date code standard, process improvements, and now we've got empirical evidence. And not just Rochester, there's also a TI white paper out there that says the same thing. I think Allegro and lots of people have started moving to 5-year date code, very common, very easy to say. At Rochester, 15 for us is an absolute no-brainer. So. Okay, and let's link this in now to traceability. If you've got traceability on a product and you've constantly and you can prove that it stayed within AS 6496 fully authorized channels, now you have an auditable channel, you have insured storage, and now we've got data that says, hey, there's no problem here with date code product when you're doing board attach work. And so the industries that matter here when it comes to traceability, you've got different standards. You've got everything to do with aerospace, and of course they FAA and EASA regulations, traceable components for flight safety, medical devices, ISO 13485, IETF 16949, combining into an ISO standard, but on traceable semiconductors for automotive. And you've got all these standards kind of pushing toward traceability being important. That should blow out any date code requirement if everything is traceable and fully authorized. Just because you have traceability through an independent distributor channel doesn't mean you know how the product was stored. Yes, you've got traceability, but that's not AS6496. That's just who touched the product, but that doesn't say how the product was stored in that channel. And that matters. So some conclusions here. We've got a bunch of things coming into market consolidation and the last or product consolidation, I'll say, and end of life. The last thing we want to do as Rochester when we have the last of products is to have somebody come in and say, hey, we need you to do dip and look on that. And then we toss good product. That's what we want to avoid. We want to get rid of the older ways of looking at long-term fully authorized stored product because it might be the last product that ever exists and you're going to have us go do dip and look. That's fraught with, whoops, we might be throwing away the last of something that ever exists. And so we don't want the industry to stay locked on the old ways of viewing solderability, the old ways of looking at date codes. We need to move away from that. You know, they don't. It doesn't indicate component quality at all for date codes that have been stored in an authorized manner. But contract manufacturers have a problem. They absolutely have a financial challenge coming at them if they can waive all kinds of date code. Who's going to pay for that stock? How's that stock going to get paid? How is all that going to work out? That's a real problem for the industry to tackle. But purchasing from authorized distributors, knowing that the product has never left the authorized channel, very effective to mitigate against unknown handling, unknown storage, and ensure full traceability. We've conducted this detailed analysis. Peter gave highlights of the 3 different papers that we've done, and we see that up to 22 years, no issues or failures detected when properly stored and using the board attach method now found in that last standard there, the E version of that J standard 002. Multiple OCMs, it's not just Rochester anymore. So we've actually made great inroads with ECIA and JEDEC, where we have audiences now, and we're working toward trying to get the whole discussion about fully authorized date code addressed in a different way, because there really isn't a standard. Where this all came from before with 2-year, 3-year, 5-year date code is kind of each company making up their own thing. It's not really a standard. And so what we're hoping for is the industry actually kind of steps up a little bit and says, no. We've got data now from Rochester, TI, and others that says it's at least this. And we're trying to be in that discussion and drive that forward. Last slide, and then we'll go on to some questions. You know, we're really Rochester has been around 45 years now, and we were a key contributor to the development of the AS6496 standard for good reason. We believe that by our inventory being 100% AS6496, 100% never leaving the authorized channel and coming back. We don't do overstock buybacks and all that kind of thing. Even in unopened boxes, no, too late, it left the authorized channel, we're not taking it back. We believe that we're trying to establish leadership here in a way that we haven't before, and that is to actually push the industry toward long-term, properly stored, fully authorized product and date codes being pushed out in time. And we're doing the best we can with industry collaboration, customer education, whenever called upon. And I think this is the first time we're seeing Rochester actually step into these standards like this and try to drive something. So with that, Bill, I'll take it back to you for questions, okay?
Sounds good. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the Ask a Question box and hit the send button. Also, please take a moment to complete the feedback form, which will appear on your screen at the end of the webinar. To start with, were your parts in long-term storage for your white paper evaluation stored with desiccant and vacuum packaging? If not, and your study found no reliability issues, would adding desiccant and vacuum sealing adversely modify your results?
I'll take this one, Dan. So good
Okay.
question. Yeah, the parts taken out of long-term storage were stored in accordance with J Standard 020 and 33. So there would have been moisture barrier bags, desiccant, humidity indicator cards, etc. Appropriate for the MSL level.
Okay. How do customers know if the components they purchase are compliant with the traceability requirements of AS6496?
I'll take that one, Peter. So, well, if you're buying from Rochester, they always are. But if you're buying elsewhere, you have to dig in and ask for that traceability. You have to ensure yourself, unless they can say that the product was fully authorized. If you're buying direct from Arrow, if you're buying direct from Avnet, and not their broker or not their broker divisions, if you're buying direct from them, those are great examples of everything they have is fully authorized. They're the world's largest distributors. So if you're buying from Arrow and Avnet, that's going to be a 6496. And indeed, Arrow was very much, and Avnet were very much part of creating the AS 6496 standard. If you're buying from their broker divisions, no, absolutely not. You're likely not. Maybe not. But you got to dig in and you got to ask the questions, and you have to know who is always authorized and who is not. And I think that's just your supply chain intelligence that you're going to have to invest in.
Okay. Based on your study, why do you think board attached testing is not more widely used?
So great question. So one of the difficulties with board attached testing is you have to have specific boards that match the LAN patterns of the devices you're looking to test, right? So if you're testing a 48 lead TSOP, you have to have a corresponding board that can accommodate it. So when we talked about the advantages of dip and look being readily available, it's a quick test that can be done, but board level mounting is more representative, but it does take more effort and more cost.
Okay. Is there any concern with long time storage of parts now that many have copper wire bonds and not gold?
That's a good question. We'll have to review that one and get back to you. We didn't really look at that in the study, so I'm not able to provide a answer at this point in time.
Yeah, I'll add to that, Peter, that when you go back as far as we went back, which was really the window was 5 years to 22 years, that did not cover any copper product yet. And so I think that's a good question for in the future. I think we're going to have to find the answer to that. But I'd say we don't have the data yet. So there simply isn't aged copper bond wire product yet in a lot of quantity. Not quite there yet.
Okay. Here's a similar one. Did you happen to test with tin bismuth finish?
No, we did not.
Okay, that's an easy one. All right, next. For customers who still adhere to date code restriction requirements, what can be done to educate them in the reliability of components with older date codes?
Yeah, I think we've kind of participated in that. I think a conversation of around all the white papers that we've done, and also TI's white paper goes into great detail as to what they did as well. They did things a little differently in theirs, but still came to a conclusion about 17 years. I think it's really just providing data. And honestly, if a customer has contrary data, we haven't seen it. So in other words, if they had, oh, I used 4-year date code one time and I got burned, we haven't seen that data. And it'd be interesting to get that actual data from people, because we've never seen it. And anytime we've pushed back on like, why is this an issue? It all well, that's the way it was always done. That's what we've always said. That's what our company rule is. And there might be some ancillary tale from 20 years ago where they got burned on something, but no real relevant current data that we've seen that there's a aging issue.
Okay. Does Rochester Electronics offer device solderability testing?
Yes, we do. We have both dip and look and simulation reflow available. A1, B, B1, S1. So basically, accommodating tin lead and lead-free finishes in both dip and look and simulation reflow.
Okay. If we have material that has been in our inventory for an extended period of time, what would you recommend for evaluating it?
Well, I'm gonna say, we used to have a gentleman in my design team, and a brilliant guy. He retired, and he would always say, "It depends." And I think that's the answer here too, because it depends. It depends a lot on where did you buy that product? What do you have for certs on that? Did it come with CFCs from the original manufacturer, or was this bought on the open market somewhere? It begs a lot more questions. There's not really an easy answer, automatic answer. That it required digging into all the details around the product.
Well, I'm afraid we've run out of time. For those questions we didn't have time to answer, we'll get back to you via email. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank Dan and Peter for an excellent presentation, Rochester Electronics for sponsoring today's webinar, and of course, all of you for joining us. Have a great rest of the day.
Thank you all.